right, so let's define increasing functions and decreasing functions. Well, I think in this case a picture would help a lot to distinguish between an increasing function and a decreasing function. I mean, just observe the shape of the graph and, well, notice how the y values get, for the first picture, the y values get bigger and bigger as x increases. That means that's an increasing function. And for the second case, well, notice how the values get smaller every time. That means decreasing function, but we need a more formal definition to describe the increasing, decreasing, and that is in terms of the derivative of the function, right? Because, well, for example, if the first derivative is positive, then f is increasing. So that's the whole idea. Well, so how do we connect this with the corresponding graph? For example, so number one, recall that the derivative of a function tells us the slope of the tangent line at a given point. So for this function, well, at one given point, find the slope. Find the slope of a tangent line. Notice that tangent line is going up. It has a positive slope. At another point, it also has a positive slope. At another point, it also has a positive slope. Well, that means positive derivative means positive slope, which also means increasing. However, on the other hand, if f prime is negative, then f is decreasing, and we can see this in the graph. Choose any point, trace a tangent line. That tangent line has a negative slope, it's going downwards. And another point, for example, right here, trace another tangent line, trace another tangent line. So we have negative slopes in this situation. So f prime, which is slope, is negative. That's related to a decreasing function. All right. First derivative test for local extrema. So last time, or rather, yes, I think it was Monday rather, we discussed finding maximums and minimums of a function, but we did that by looking at absolute extrema, that is a function constrained to a given interval. So in this case, we're going to analyze the function to its entire domain, not just an interval. So here's what we have to do. Find the critical values, number one, which we know how to find at this point. So we set we find the derivative, set the derivative equal to 0, solve the equation, and those values of x are going to be the critical values, which is the values of x for which we will have slopes equal to 0. That is horizontal slopes, which means either a maximum or a minimum. But back then we didn't describe how do we determine that indeed it's a maximum or a minimum. So we just look at a graph, and from there we determine, oh, it's a max, it's a min. So now we're going to do this in an analytical way. So we find the critical values for the values of c that are equal to 0 or for which it is undefined. In the situation in which we have a rational function, the denominator equal to 0, that's essentially making our function undefined, or the derivative rather undefined. And then we're going to draw an analysis line, and we're going to plot those critical values on the number line to check the behavior of the derivative of the function. And then, well, so we're going to do a table. Well, I already have everything prepared in terms of a table. If the derivative goes from plus to minus, I mean it goes from increasing to decreasing, well, the behavior is going to tell us that we have a maximum point. But otherwise, if it goes from negative to positive, well, essentially this is describing a minimum point in this case, right? If for some reason there is no sign change on either side, well, then that critical value is not going to describe a local extremum. So there's neither a max and nor a min. And in some cases, even if you have increasing to decreasing or decreasing to increasing, that might be a little tricky. That doesn't necessarily imply the existence of a maximum or a minimum respectively. Because we will have some restrictions on the function, but well, that's something we're going to look at later today. All right, in the meantime, how about we go over one example here. So for the function f of x equals x cubed, x cubed minus 12x plus 1. Number 1, find all the critical values, that is, the values of x that correspond to horizontal tangent lines, and these values occur when the derivative is 0. So let's find the derivative of this polynomial function. So f prime of x equals, isn't that a 3x squared minus 12x? Minus 12 only, rather. And then from here, this is what we're going to do. So we're going to set the derivative 3x squared minus 12 equal to 0 and solve the polynomial equation for x. So 3x squared equals to 12, x squared equals to 12 over 3, which is 4, and x equals plus or minus the square root of 4 by using the square root property. And well, that's a nice root, that's a nice number. X equals plus or minus 2. So that means we're going to have two critical numbers. Number 1, x equals to negative 2, and x equals to 2. So this is something, again, that we did back on Monday, finding critical values. But we use that just to find absolute extrema on a function that is defined on a closed interval, not at its entire domain. So we're going to do the following. We're going to use the values from part A to find open intervals for which the function is increasing, and the open intervals on which the function is decreasing, if any. All right? So this is what we do. Let's draw the number line. Let's draw a number line and plot these numbers, negative 2 and positive 2. Alright, so when we divide the number line using these two critical numbers, notice how this gives rise to 1, 2, and 3 intervals to test, right? So we need to check the sign of the derivative here, we need to check the sign of the derivative here, and we need to check the sign of the derivative here. And well, I highly suggest to create a table like this, so you can have all the analysis like to every single detail. I'm going to show you how to fill in this table step by step. So I had 3 empty columns. Each column corresponds to each region that we test for increasing, decreasing. So number 1, let's describe each interval. So the first interval, that stops at negative 2 but goes all the way to negative infinity, so that's from negative infinity to negative 2. Alright, that's the first interval. And then the second interval, it's the interval between negative 2 and 2, exclusive on the endpoints. And the third interval is that interval that goes from 2 all the way to infinity. Alright, so those are the 3 intervals to test. All right. So we're going to choose test values contained in these intervals. And guys, choose the easiest number possible. All right, the smallest number possible. So a test value here in the first interval. Choose any number between negative infinity and negative 2. Negative 4, alright, negative 4. Any number between negative 2 and 2? 0. That's the easiest one. What about between 2 and infinity? 4, alright, or 3, that's fine. Either way is fine. Okay, so we're going to test each critical value. So we're going to test negative 4, we're going to test 0, and we are going to test 4. Where do we test them? Very important. in f prime in the derivative, because we want to know the behavior of the derivative. We want to know based on the sign of the evaluation of these values, of these values of x, of these critical values, to determine, well, the test values rather. These are not the critical values. This is just the test values. So we need to know if positive then increases, if negative then decreases. So that's what we want to know here. So let's plug in our derivative. Let's plug in these values in our derivative, which is 3x squared minus 12. All right. So this will be 3 times negative 4 squared minus 12. All right. So that's okay. Negative 4 squared, that's 16. 16 times 3, is that a 48? And then 48 minus 12, that's 46, 36. But what is this 36 ultimately? Is that a positive number or a negative number? It's positive, so this is greater than 0. That means positive, all right? We can fill in the blank for that corresponding cell right here. Let's test x equals to 0. 3 times 0 squared minus 12. And well, 0 squared is 0 times 3, it's also 0, but 0 minus 12, that's a negative 12. In this case, it's a negative number. All right, that's a number less than 0. So the sign of f prime is negative here. All right. Well, let's test x equals to 4. So that's 3 times 4 squared minus 12. And well, that's essentially the same number as before. So 4 squared, which is 16, times 3, that's 48, minus 12, 36. And that's a number greater than 0, which means it's a positive value. All right. So we are going to draw conclusions based on the sign of the derivative using the test value. Well, in this case, since the sign of f prime, that is the sign of the derivative, is positive, that means the function is increasing. If negative, it's decreasing. If positive again, it's increasing. So what are we going to have? So let's go back to our number line. Well, the first interval, increasing, means we're going to have this shape. We're going to go up the hill. The second interval, which happens to be decreasing, goes down the hill. And the third interval, which is increasing, goes up the hill again. Well, we're going to use that chart, or that number line rather, to look at the behavior of the function in this case. All right. So notice how it goes from increasing to decreasing, and then from decreasing to increasing. This means that x equals to negative 2 will be a relative maximum, and this means this will be a relative or local minimum. All right, so we're going to have a maximum and a minimum. All right, so let's confirm this, and let's actually find those values of the maximum and the minimum, because they're not just telling us whether there is a max or a min. They're also asking us to find the values. And well, what do? Go back and plug the critical numbers in the original function. All right, so relative maximum, so that's going to be when number 1 in f of x in this case, right? Not in f prime like before. So that's going to be f of negative 2 and f of positive 2. So that means we're going to plug in negative 2 and 2 in the original function. So that's negative 2 cubed minus 12 times negative 2 plus 1. Well, we have the information here from the graph instead of computing the numbers, so it's 17. And what else for 2? That's 2 cubed minus 12 times 2 plus 1. So the y value corresponding to 2 equals negative 15. And well, here I have the graph of the function that we just analyzed, and it's showing all the information. See how it is increasing from negative infinity to 2, as in the table above, as in the chart above. Let me zoom it out. So yes, so increasing. So this arrow means that it's going all the way to negative infinity in both directions, the x direction and the y direction. And well, it's increasing from negative infinity to 2, then decreases from negative 2 to positive 2, and then increases again from 2 to infinity. So all this analysis that we did algebraically and numerically confirmed what is confirmed by what we have in the chart right here. All right. And well, so that's our first example on how do we find maximums and minimums, and how do we analyze the intervals for increasing, decreasing. So that's pretty much everything about the first derivative test. Again, in summary, the first derivative test is to analyze a function and determine whether it's increasing or decreasing, and based on that information to determine if we have a maximum or a minimum value. All right? So let's discuss concavity and the second derivative test. All right. So concavity, so I think a picture again is going to help. So when we have a parabola that is upside down versus a parabola that is opening up, the first case, the first graph is that of a concave down, because opens down, and concave up. And well, to distinguish between the two, or to kind of a shorthand rule, you can abbreviate concave up, just write cup. All right, and this looks like a cup, right? Cups are concave up, right? So that's one way to distinguish between concave up and concave down. Well, what's the criteria for concavity? Well, if the second derivative is positive, then concave up. If the second derivative is negative, then concave down. All right? Just like in a similar way that for increasing, decreasing, positive slope increasing, negative slope decreasing. Positive second derivative, concave up, negative second derivative, concave down. All right. Let's discuss the second derivative test and how do we determine points of inflection. Those points of inflection are going to be the points where the graph changes from concave up to concave down. Okay, let me do another graph. So this point is a point of inflection. This is another point of inflection because this is the part of the graph that goes concave down. At this point, the graph changes from concave down to concave up, and then at this other point, the graph becomes concave down once again. All right. Those are the points of inflection, also known as turning points. You know, the graph turns from concave up to concave down, or vice versa. Well, how do we determine those points? So in this case, because it's related to the second derivative test, well, naturally we'll have to find the second derivative of the function. Well, and we will have to find critical numbers or critical values, but in this case from the second derivative. However, we have a special name for the critical numbers that come from the second derivative. We call them hypercritical values, because if we say critical values, it wouldn't be clear whether those numbers come from the first derivative or the second derivative. So we need to have some vocabulary to distinguish between critical values of the first derivative and critical values from the second derivative. So the critical values from the second derivative they're called rather hypercritical values. And it's the same process. Take the second derivative, set it equal to 0, solve the equation for x, or c, whatever it is, for x. And then we're going to do some analysis again based on a number line when we cut that number line using those hypercritical numbers. But in this case, instead of checking increasing, decreasing, or decreasing, increasing, we're going to check concavity, concave down or concave up. So I think an example is just going to be better than looking at all these symbols and definitions. Of course, we're going to go back to these definitions to check our work and check the consistency of all these ideas. All right, example number 2. For the function f of x equals to x cubed minus 3 halves x squared plus 5. Determine the interval on which f is concave up and the intervals on which it is concave down. And then, if any, locate any points of inflection. And that usually happens when there is a change in the concavity, but not always. That's something that's going to be tricky, and I'll let you know what the situation is with examples. All right, so let's find, well, in this case, for hypercritical values, we're not going to use the first derivative. We're going to use the second derivative. So first, we need the first derivative, of course. So that's 3x squared minus 2 times 3 halves x. And the derivative of 5 is 0. So this is the same as saying 3x squared minus 3x. That's only the first derivative. The second derivative, however, f double prime, that's going to be 6x minus 3. And this second derivative, we need to set it equal to 0. 6x minus 3 equals to 0. 6x equals to 3. And x equals to 1/2 in this case. All right? So that's our critical number. In this case, we didn't get 2 critical numbers like the previous example. We got only 1. So number line, and slice and dice the number line using these critical numbers. All right. Well, hypercritical numbers. In this case, 1/2. That's our only hypercritical number. And well, when we chop our number line into one critical number, that gives rise to 2 intervals to test. All right. And for this reason, I have this table with 2 empty columns for each test value. So number 1, let's define the intervals. So number 1, the first interval comes from negative infinity and stops at 1/2. And the second interval starts at 1/2 and goes all the way to infinity. Exclusive in all cases, all right? So we're going to choose our favorite test values. Okay, so let's choose a test value in this interval between negative infinity and 1/2. Use the easiest one. 0, all right? 0 is a great candidate. What about in the second interval? 1, great. I mean, of course, you can use negative 5 million and positive 75 zillion if you want, but it doesn't need to be numbers that big, all right? Choose the easiest as possible. All right. So this is what we're going to do. We're going to test those hypercritical values. X equals to 0 and x equals to 1. Where are we going to test this? Oh, again, careful. Test this in f double prime, because we're looking at the second derivative test, all right? So we're going to look at the end behavior of the second derivative. So let's look at the second derivative. That's 6x minus 3, all right? So that's 6 times 0 minus 3. That's a negative 3, which means it's a number less than 0. And when the sign in this case is negative, well, we'll figure it out in a minute. Test x equals to 1. 6 times 1 minus 3. That's 6 minus 3, which is 3. That's positive. Let's put positive here. All right. Well, what's our conclusion when the second derivative is negative? In this case, when the second derivative is negative, this is concave down. And when it's positive, it's concave up. All right. Let's describe this graphically. Concave down. Have a sad face for concave down and a happy face for concave up. All right. Now, is there a change in the concavity? Is f of x going from sad to happy or from happy to sad in this case? So that means there is a point of inflection, right? There is that function f of x has a turning point. And what's going to be that turning point? Well, the point where x is 1/2 and y, well, that's going to be from the original function. So in this case, there is a point of inflection. So how do we find that point of inflection? Well, point of inflection in f of x, in the original function. So we're going to go to our original function, which is here. Evaluate f at, what was that, 1/2? Our hypercritical value, that is 1/2 cubed minus 3/2 times 1/2 squared plus 5. And well, after doing all these calculations, well, in fact, we have that y value of this point of inflection, which in this case is 19/4. All right. So again, let's observe the graph. So this x value of the turning point right here is 1/2, and that was the value of our hypercritical value. So what's the behavior before that hypercritical value? Well, doesn't it look like concave down? And what about past the hypercritical value? Doesn't that look like a cup, concave up? All right. Is that consistent with what we have back in our table before? Concave down to concave up? All right. So we can always check our work for consistency with our analytical process and the graphic process. All right. Are you guys following me here? Is everything making sense so far? All right. Let's do a bunch of examples. So the good thing is that we're going to spend actually 2 lecture sets today and Monday's lecture looking at max and mins, looking at many examples, because some situations, some functions may get tricky at times. So we want to make sure that we cover at least one example of each. The first couple of examples are these examples in which everything worked really nicely. But what about example number 3? So let's analyze. So for now, I'm not going to write the whole thing. Find the intervals in this block. No, just analyze. And by analyzing a function, it means the whole thing. Find intervals in which increases, decreases, and max and mins, if any, and find the intervals in which concave up or concave down, and points of inflection, if any. So, but the thing here we're going to do, I'm going to split the problem into essentially 2 parts. Number 1, the first part is essentially everything concerning the first derivative test. So let's find the first derivative. F prime of x equals to 6x squared minus 4x cubed. So we want to find the critical values. And we get the critical values by setting the first derivative equal to 0. Well, we need to solve this equation to get those critical values. So this is a polynomial equation for which I think we can factor the greatest common factor. That is the lowest power of x, which is x squared, and between 6 and 4, I think we can factor out a 2. That's going to leave us with 3 minus 2x equals to 0. So from here we're going to use the zero product property. That is either 2x squared equals to 0 or 3 minus 2x equals to 0. Solving this equation, we'll divide both sides by 2. It's still x squared equals to 0. Take the square root on both sides. That's still just going to be, well, plus or minus 0. Well, there's no such thing as plus or minus 0. 0 is just 0. All right? It doesn't have a sign. And what about here, the second equation? So that's negative 2x equals to negative 3 and x equals 3/2. So these are our critical numbers. So we're going to slice and dice our number line. Over our critical values, 0 and 3/2. All right? And again, when we plot these two critical numbers in our number line, this will give rise to 1, 2, 3 intervals to test. So we need to describe each interval so we can choose our test value accordingly with each interval. So number 1, the first interval is going to be negative infinity to 0. The second interval goes from 0 to 3/2. And the third interval from 3/2 to infinity. So let's choose our favorite test values. All right, what about in the first interval? -1. What about the second interval?
0.
Well, we cannot use the critical value. It has to be a number between 0 and 3/2. 1/2. Well, how about 1? Because it's integer. I mean, 1/2 is fine, but when it comes to plugging into the function, that's going to be an issue with the fractions. And then between 3/2 and infinity, about 2. So we're going to test x equals to -1, x equals 1, and on the next page I have a space to test x equals to 2. All right, let's do one at a time, and we're going to test again in f prime of x, in the derivative, because we want to see the end behavior of the derivative to determine whether it's increasing or decreasing based on the sign of the derivative at those test values. So the derivative is 6x squared minus 4x cubed. So that's 6x squared minus 4x cubed. That's -1, -1. Well, in this case, so -1 squared, that's +1 times 6. Is that +6? And then be careful here, because -1 cubed is -1. -1 times -4, isn't that +4? Which is 10 in the end. That means this is positive, right? Because this is greater than 0. What about testing the next test value? So 6 times 1 squared minus 4 times 1 cubed. Well, so that's 1 squared, which is 1 times 6 is 6. 1 cubed is 1 times -4 minus 4. That's 2, which is also positive. All right, you'll see what happens in this situation in a minute. So, and testing the third. So that's 6 times 2 squared minus 4 times 2 cubed. Well, so 2 squared, which is 4, 4 times 6 equals 24, and 2 cubed, which is 8. 8 times 4, that's -32, and 24 minus 32, isn't that a -8? Which in this case is a number less than 0, which means the derivative is negative. All right. So let's find conclusions about the derivative about f prime based on the sign. The sign of f of x is positive. What does that mean? Increasing or decreasing? Increasing. Increasing. Minus decreasing. Alright, let's put that into picture. So, first goes up the hill and then goes up the hill again. Interesting. And then in the end goes down the hill. So in this case, well, for the first critical number, neither max nor a min, because there's no change from increasing to decreasing nor a change from decreasing to increasing. So it's going up, it's stopping, and it's going up again. You'll see how's that going to look on the graph. However, for 3/2, because it's increasing and then decreasing, what's this shape of a max or a min? A max, right? Rel max. Relative maximum. That's what rel max means. So I'm just using shorthand so it's quicker. All right? So we can go ahead and find that relative maximum. So relative maximum, that's in the original function f of x, not in the derivative, not in the second derivative. So it's in the original function. So we're going to evaluate for the maximum the original function at 3/2. Okay, what's the original function? Okay, so f of 3/2 equals 2x cubed. So 2 times 3/2 cubed minus 3/2 squared. All right? Oh no, to the 4th rather. Okay, so actually let me do this one in the calculator. So I believe I typed the function already. No, I don't think so. Yeah, it's still in parametric. I don't know why. So what was that? 2x cubed. So 2x to the 3rd minus x to the 4th power. And well, let me first quit. Let me compute the value. Bars, y bars, function, y1 evaluated at 3/2. And go math, frac to get the exact value. 27/16. Alright, so this is 27/16. So as an ordered pair, that's 3/2 comma 27/16. Relative minimum. Did we get a relative minimum in this case? No, that's the only thing we got, a rel max. So not applicable for relative minimum. All right. Okay, let's continue this exercise towards the second derivative test. So let's find the second derivative. So the first derivative is 6x squared minus 4x cubed. The second derivative should be f double prime 12x minus 12x squared. 12x minus 12x squared. And set it equal to 0. 12x minus 12x squared. That means 12x times 1 minus x equals to 0. When we use the zero product property, that's 12x equals to 0, or 1 minus x equals to 0. Here, x equals to 0 and x equals to 1. So these are going to be our two hypercritical values. And when we plot them on a number line, this will give rise to 1, 2, 3 intervals to test. So that's why I have 1, 2, 3 empty columns, 1 for each interval, 1 for each test value. So Here the interval will be, number 1, negative infinity to 0, 0 to 1, and 1 to infinity. Alright, so let's pick our test value. So what would be a good test value for the first interval? -1. What about in the second interval? 1/2. So in some situations like this one, when our critical numbers are consecutive integers, there's no way around, we will have to use a fraction. So hopefully it doesn't go that crazy. And what about a good test value in the third interval? 2. Alright, so let's test -1, 1/2, and 2.